Good afternoon. I'm very glad the rain stopped so that you could join us for a little while. I'm very happy to tell you about the Tokamak. These are the questions I'm going to probe today. And these, at first glance, seem very basic. But, you know, I had to talk to quite a few people in the Tokamak to get the answers to these questions, because I wasn't even sure. So anyway, what is a Tokamak? Very basic question. Why is the ITER Tokamak so big? Why do we have so many big superconducting magnets? You know, they're a big problem. Why do we have all these things? Why do we have both a vacuum vessel and a cryostat? You know, it's not so obvious. You know, what do the blanket and diverter do? How can you assemble a machine like this? Remote handling? You know, why is it so important, which it is? And then, why is the design of the ITER machine so challenging? So, by the end of this talk, I'm hoping you all can remember the answers to these questions. What is a tokamak? Well, first, this word tokamak is an odd word, and a lot of people aren't familiar with it. It's an acronym, a Russian acronym, and it basically means something like toroidal chamber with magnetic coils. It's a Russian acronym because our Russian colleagues back in the 50s invented this tokamak concept. So they started it all off. It wasn't soon after it was developed back in '56 that around the whole world it was clear this is the right way to go with magnetic fusion. So soon everyone was building tokamaks. There's a long history here of things. What we're interested in is when we got to 1985, there was a proposal at a superpower summit, I think a lot of people know, to actually kick off this project called the ITER. That's where it all started. So just a couple more words on the tokamak and basically what it is. You know, a tokamak is something that with this configuration has toroidal magnetic field coils to produce magnetic field a certain way. Plasma current produces colloidal magnetic field. You have all these magnets in this basic configuration, and that's what we call a tokamak. Okay, and you all know what tokamaks generally look like. This is ours. It's very familiar to you. But I wanted to at least put up one picture that shows the current biggest tokamak in the world, which is the JET facility in England. Show what the inside of this looks like on really an operating tokamak. You know, it looks like this, and our plasma chamber will look very much like this, although obviously bigger. And when you have a plasma operating in here, it looks like this. So we're going to have something very similar to what's been operated around the world. Ours is, of course, bigger. We're going to have much higher power, 500 megawatts, and we're going to have the high temperatures in the plasma chamber, just like everywhere else on the planet that runs tokamak. Why is the tokamak so big? Well, just to start out with how big it is, it's quite big, and this picture is to scale. So I like this picture because this is out in front of building 519. So we all are familiar with how tall that building is. It's a two-story building. Its height is just about 5 meters. So the tokamak is almost 30 meters. So whenever you look at 519 the next time, think of the tokamak being almost 6 times taller than that building. So the tokamak is very big. Another comparison I've used from time to time is, you know, this famous monument we all know in Paris, which is very, very monstrous. We're about 60% of the height of that monument. Now, if you compare on the basis of mass, you know, I talked about size so far, but mass, how heavy it is. The ITER tokamak is about 23,000 tons. Now, when you compare the mass of the tokamak, you have to compare it to something very big, like a ship. Is really the only thing you compare it to. So, if you take the largest ship in the French Navy, which is the Charles de Gaulle aircraft carrier, which is 38,000 tons, you can see we're about 60% of the mass of this aircraft carrier. So it's extremely massive. So the ITER tokamak specifically is so big because of this ignition margin and fusion power. We want to produce 500 megawatts of fusion power. And this capability to produce fusion power increases with the plasma current and the toroidal radius. So what that means is the distance from the middle of the machine out to the center of the torus radius. If you want to produce more fusion power, it must get bigger and bigger. So these are the machines that have been operating around the world over the last 50 years or so. And as you move to the right, you can see they get bigger. This is the JET machine, the current biggest one in the world. Here's the size of the ITER plasma chamber. And with that size, because that radius and the cross-section of the plasma needs to get bigger. So this is ITER again, 500 megawatts, where of course we're heading is to this reactor which we call demo. And so to get even more fusion power, once again, you have to get the radius bigger and the plasma chamber has to get bigger. So it's just as simple as that. Now if you talk to David Campbell, who's in our physics department, he will fill 2 pages of equations to tell you the same thing. But basically, it's this radius and the plasma chamber. Why do we have so many big superconducting magnets? First off, how many do we have? We have a lot. We have 48 superconducting magnets. TF coils, these ones shaped like an oval sort of, we have 18 of these. PF coils, we have 6. We have correction coils, we have central solenoid coils, so we have lots of coils. And just a couple of facts about the coils. As I said, we have 48. They are also very massive, 98,000 tons. There are a lot of large ships in the world that are smaller than 98,000 tons. If you look at the conductors that we put in here, the basic wire, something like nearly 200 kilometers of wire. We have very high fields, on the order of 10 Tesla, very high currents running through these magnets, 68,000 F. And there's a lot of storage energy, 51 gigajoule, and we'll talk about that later because no one knows what a gigajoule is, but we'll talk about that. And just a couple of things on challenges. These pictures look very nice and simple, but what are some of the real challenges with the magnet design? And just 3. If you talk to the guys in the magnet division, there'll be a list of many, many pages, but some of the extremely important challenges from my standpoint are QA/QC. This is such an integrated structure that if you have something buried down in here, anything, a piece of wire, a structure that's not been manufactured exactly right, and if we don't find out about it until we assemble this together, we operate, it fails, we are in big trouble because it's going to take months, even years, to take this back apart and fix it. So we can't afford that. So QA/QC, where these are manufactured all around the world, is critically important. Another challenge we have are tolerances. To get all this to fit together just right, we have to have very tight tolerances. And anything this big, with tolerances of less than a millimeter, in some cases much less than a millimeter, is a big, big challenge. And of course, schedule. We talk about this all the time. Producing anything like this on schedule is always a very difficult challenge. Okay, so a little bit more on size of the magnets. This is 1 TF coil. We have 18, as I said. 1 TF coil weighs about 360 tons. Now, if you want to compare that to something, a Boeing 747-300 at maximum takeoff weight, so this is full of people, full of fuel, is almost the same as 1 TF coil. So this is very, very heavy. And just a sideline, this is one of the components that drives these roads that are being modified out here that have been holding up traffic for all of us for the last year. It's not the heaviest one, but it's one of the heaviest. We have some of the ones that drive these roads from a weight standpoint are the TF coils, but also vacuum vessel sectors, which are even a little bit heavier. And we have 1 PF coil that is being built in Russia that's also quite heavy and big. So you take a few of these big components, including the TF coils, and that's the reason that a lot of these roads are being modified. So the picture I showed before looked very nice and simple, but in fact, all of these coils are quite complicated. They have structures inside that support these conductors. The circular things are the conductors where actually the current runs. We have other structures that hold these. It's quite a complicated thing putting them all together. And another factor is these coils are built all around the world. You have the conductor, the wire, is built at 6 of the parties, basically everywhere except India. You have the case that's built other places, put together others. So this kind of gives you an idea of what's going on. The conductor goes to certain locations where the winding is done, and then it's ultimately all shipped. But this is a big, big challenge for the magnet division to kind of coordinate all these activities. Okay, magnetic field. I mentioned that these the magnets produce fields that are on the order of 10 Tesla. Well, to compare that to something that we have a little bit of feel for is the Earth's magnetic field, which is about 1/2 a Gauss. And so that's 0.5 × 10⁻⁴ Tesla. So the field we produce in ITER is on the order of 200,000 times higher than the Earth's magnetic field. Okay, energy. So whenever these magnets are all totally powered up, they produce a lot, or they have a very high energy state, 51 gigajoules. Okay, so as I said, no one knows what a gigajoule is. So to compare that to something, if we go back to the Charles de Gaulle, 38,000 tons, if it was going 180 kilometers per hour, which of course it can't go near that fast, but if it could, that's 51 gigajoule. Now, another one that I put on just because the 180 kilometers per hour reminded me of fast driving. So I picked an Audi A5, which of course Norbert drives, I'm sure, quite routinely at 180 kilometers per hour, probably to work. And if you take an Audi A5 at 180 kilometers per hour, to get that energy of 51 gigajoule, you have to have 19,000 A5s all running at that speed at the same time. That's 51 gigajoules. So it's an unbelievable amount of energy. Okay, now to talk a little bit about the conductor itself. Now, you know, you might think this is just a kind of a fancy wire, and it is, but for ITER, it's one of the most critical components we have. It's one that absolutely has to be correct. And so we spend a lot of time making sure that, you know, the design that we have is going to meet the requirements, and they'll be manufactured to the appropriate QA standards and so forth around the world. So there are very, very critical things. So a couple of facts on these. Just for the TF conductors, these are the 18 toroidal field magnets, we have nearly 100 kilometers of this conductor. Whenever we started this procurement, it was and will be for many, many years the biggest niobium-310 conductor procurement in the history. If you take all these little tiny wires that make up this conductor, if you put them all together, you go around the Earth about 15 times. So there's a lot of wire involved. Operates at cryogenic temperatures, of course, about 5 K. The field is up in the neighborhood of 10 Tesla, again, high currents, and manufactured by everyone. So I wanted to show one thing about the status of this conductor, because this conductor is one of the leading activities on ITER. In other words, there's actually work going on at the different parties right now on producing this. And to give you a first-hand look at this, just one example is this, what we call TFPF winding building that has been built in China. If you look at the inside, it's a very large, impressive building that you can't see well in this picture, but there are winding machines back here, there are compaction machines, and coming out of the end of the building, we've got this jacketing line, which is an important way that we put this outer case on, and this jacketing line goes on for almost a kilometer out of the end of this building. It's quite impressive. So I'm going to show if I am successful here at getting a little video up. I'll show you a video of the winding. So let me see if I am successful here. This is a winding machine in action. The picture I showed before, there are 5 lobes, if you will, in this conductor, and this is putting them all together, winding, twisting them together into one cable that comes out of the other end of this machine, wound together. Then it goes through this machine, which compacts it. Then it goes on to the right a little farther, goes through another machine. The stainless steel wrap has been put around it, and then we're going to put it on a roll, and that roll is how it's transported to the next place where we'll put a jacket on. Okay, so a little bit more on magnets. Going on to another very important magnet, which is the central solenoid. A few parameters here. Once again, it's made of the same conductor, high fields, high currents. It's very heavy. This stack, when you put it all together, which we will do here, this will be manufactured in the U.S., weighs about 1,000 tons. It's not the biggest lift we have, but it's one of the biggest lifts. So if you talk to the people that are designing the building, putting together the cranes, they have a very large crane, 1,500 tons, and this is one of the big components that we'll be putting in. There are a few others that ride up at nearly 1,500 tons, but this is one of the big ones. Okay, I think the last coil I'm going to talk about is the toroidal field coils. These coils are very big. We have 6 of them. Most of them are so big that you have to manufacture them on site. They're too big to transport. There is one that you can just barely fit on the roads, but most have to be built here. So we're going to build a building on the site that's very large, 250 meters long, 45 meters wide, to do the assembly of these PF coils. And it's going to be probably the first building on the site. Okay, so the answers to the questions. We have so many big superconducting magnets because, well, first, the number we have, we need so many because we've got a lot of functions that we have to perform. TF coils provide the toroidal field. PF coils are used to shape the plasma, control its position. Central solenoids used to drive the current in the plasma. And then we have correction coils, which are used to correct small field formations, which turn out to be very important that we correct them from a refinement standpoint. So we have big magnets, really, to go around the plasma. It's as simple as that. And the first wall. So that drives the size. And you have to have this field over this large area, but it's driven by the size of the plasma. And then we need superconducting magnets, really, to maintain field efficiently. If you didn't have superconducting magnets, which are very, very efficient at carrying high currents, you would have lots of heat generated. There would be a lot of expense associated with operating this machine. So it's efficiency of operating the magnets that drives it with the superconductor. Okay, so now I'm going to shift to the vacuum vessel and the cryostat. So why do we have both of these things? First, what they are. So this is the whole Tokamak, the vacuum vessel, is the torus-shaped chamber that fits in here, has all the ports around, as you can see here. And the cryostat is this separate vessel that goes around and encloses the entire Tokamak. So that's what we're talking about. Just a little bit on the vessel. The vessel also is very big, very massive. If you take a look at, if you weigh the vessel and the components inside, it's about 8,000 tons. Compare that to the Eiffel Tower, which is only 7,300 tons. So this has a lot of steel, as you can tell. So a couple of facts about the vessel. The vessel is the first safety barrier, which is very important for this project. It's made of stainless steel special grade. The weight of just the vessel by itself is still 5,000 tons, size you can see there. We have both of these because the vacuum vessel is required to provide the vacuum boundary for the plasma, critically important, of course. It's required to shield the magnets, which we have to keep at superconducting temperatures. So the shielding function for the magnets is very important to the vessel. And it's the first safety barrier. The cryostat, there's not a cryostat on every fusion device you see around the world. But it's required on our machine because we have superconducting magnets at 4K and we have to provide thermal insulation around them. And that's the reason we put this vessel around the outside and then we can evacuate this area that's around all the coils. Because if you have air in there, you'll have condensation, you need insulation. And so you need to evacuate that chamber to get the insulation. Okay, so what did the diverter and blanket do? First, the blanket are these structures that go on the inside the vacuum vessel here, face the plasma. The diverter is this device down at the bottom, also faces the plasma. Okay, a couple of things on the blanket. These modules, we call them blanket modules, you can see here. We have 440 of these modules around on the inside the ITER Tokamak. They're each about 4 tons. So you can see we've got a lot of weight there. There are lots of different ones. They aren't all the same, unfortunately, which makes our design more challenging. We have 40 different designs we have to deal with. Some of the issues with the blanket, we have very high loads, both thermal and mechanical loads on these components. So we're always analyzing to see if the structures can take these loads. They're manufactured all around the world, which is another QA problem, as I mentioned. And they all have to be handled remotely. And so these are all things that make this quite a challenge for us. Okay, on the diverter, a couple of things about that. These diverter components go all the way around the base of the Tokamak. There are 54 of these assemblies. And then on it, we have these plasma-facing components you can see here. And these plasma-facing components, there are many of them, over 4,000, made of primarily tungsten and carbon-carbon composite. So the issues are similar to the blanket. High thermal mechanical loads. QA is extremely important. Remote handling is a driver. Just one thing on materials. The 3 primary plasma-facing materials we have. On all these blanket components here, the blue that you see, this is beryllium. is our plasma basic component here. It's kind of the one that over the years has evolved as kind of the best compromise of lots and lots of parameters that you would look at to choose this material. But this first wall is beryllium, so that's our blanket first wall material. And then down here, as I mentioned on the diverter, we have areas where we have tungsten, areas where we have carbon-carbon composite. And again, different parameters drive this, whether you're looking for low erosion, which is a property of tungsten, or shock resistant, which is a characteristic of carbon-carbon composites, or if you're looking at something that doesn't perturbate the plasma when you're looking at beryllium. So these are all things that are considered when we choose these materials. So, blanket and diverter are needed too. In the case of the blanket, shield the magnets, provide high heat flux components to face the plasma, because there's certainly a lot of heat that comes off the plasma for this, which ultimately protects the vessel. And on the diverter, again, to provide shielding, but it's also to extract heat and helium ash from the plasma, and that allows a high performance plasma. So in the case of the diverter, you know, you have a plasma, it's got all kinds of things in it. You need to be recycling it all the time, taking some out, purifying it, taking what you don't want, the helium out, taking what you do want, recycling it, putting it back in. So, so that's one of the main functions of the diverter. Okay, so how can we assemble a machine like this? So this is the responsibility of the assembly group. It's a big, a very, very challenging job. And this shows the Tokamak building with the pit here, and shows where the Tokamak's going to go and at various stage of assembly. Next item, remote handling. So why is remote handling important? It's something that often you don't think about early in the early design phases, even though we should more. But remote handling is something that drives a lot of our designs. It's very important because after we run this system for a while with tritium and deuterium in the plasma, the materials become activated and you can no longer go in and work on them by hand. So you have to be able to remotely replace a lot of things, such as the blanket modules that we were talking about, the diverter. We have these cassettes are put in with special fixtures. We've got to have special viewing systems, special arms to do things, special transport casts which transport all these components between the hot cell and the tokamak. So remote handling is a critically important area. So the last question. Okay, why is the design of the ITER machine so challenging? Okay, if you ask anybody, they'll have their own list, but this is my list. And I didn't put everything down, but it'll give you an idea. From a project management standpoint, it's challenging because tight schedule, very tight budget, limited resources. We all understand that on ITER. New organization that we've been building up, 7 parties that we have to coordinate with. You know, from design and procurement, very complex design, severe QA/QC requirements, complex procurement splits, many procurement packages, and then when you get to the individual component or system level, you know, these are you know, amongst the most challenging fluxes you'll find anywhere in the world. Remote maintenance, very complex. What we're doing is more complex than almost any other remote handling activity anywhere in the world, and the list goes on, and people can, I'm sure, add pages and pages of these items. So, to my last slide. So, here's where we are. This is where we're going to go next. Got a little ways to go, but I think we're well on our way. So that concludes my talk, and I'll be glad to answer any questions you have.